Hey everyone, welcome. Today, we're going to peel back the layers on AI. We're not just talking about models that give us answers, we want models that can explain how they got there. It's all about extracting logic that we can actually understand.
So let's just imagine for a second. Your AI model denies a loan, or maybe it flags a transaction as fraud. What's the very first question you're going to ask? It's why, right? If that model can't give you an answer, you're dealing with a black box. And, trusting a black box when the stakes are high, that's a massive risk.
Okay, so that leads to a pretty obvious question. We live in this world of super powerful, really complex models like deep neural networks. So why would we even bother with simple rules? Well, the answer comes down to one word: transparency.
So think of it like this. On one side, you've got what we call symbolic models. These are basically just a set of really clear if-then rules. The logic is totally transparent. Anyone can read it. But then on the other side, you have the black box models, things like neural networks. Now, don't get me wrong, they can be unbelievably accurate, but their reasoning is buried deep inside millions of complex calculations. It's totally opaque. And the value here, it really comes from a simple chain of events. See, if a model is interpretable, it means we can actually verify its logic. And if we can verify the logic, well, then we can start to trust its decisions. And what's really cool is that sometimes that logic can show us brand new patterns in our data we never knew existed. That's a huge win for knowledge discovery. All right, so wanting rules is one thing, but how does a machine actually build them? How do you go from a mountain of raw data to a simple, insightful if-then statement? Let's get into it.
Well, the most common way is actually a pretty clever and intuitive process. It's called the covering algorithm, and it's basically a simple loop. Step 1, the algorithm finds one single high-quality rule that correctly identifies or covers a chunk of your data. Step 2, it takes that data out of the pile, and then it just repeats the whole process on what's left over. It just keeps doing this, building one rule at a time until everything is covered.
Okay, let's make this real. We'll use a classic example, trying to figure out which trains are heading east. So the algorithm kicks off with the most general, broad rule you can imagine. If anything, then the train is eastbound. Obviously, that's not super helpful just yet.
So, the next step is what's called a greedy step. And all that means is the algorithm looks at all the possible conditions it could add, and it picks the single best one, the one that gives it the biggest accuracy boost right at this moment. So, for example, it might figure out that the train has a short car is a really good predictor. So bam, it adds that to our rule.
And then, it just does it again. It asks, okay, is there another condition that could make this rule even better? Maybe adding, and the train has a closed car makes it even more accurate. The algorithm just keeps tacking on conditions until adding more doesn't help anymore. And at that point, that specific rule is done, at least for this round.
Okay, so now we have a rule. But I've been saying better and more accurate. What does that actually mean? How do we really measure if one rule is stronger than another? Well, for that, we need to talk about a few key metrics.
The way we evaluate any rule is with a simple little grid called a contingency table. Just think of a rule as, if this condition, the body, is true, then this prediction, the head, is true. This table just counts up all the outcomes. How many times were both the condition and the prediction right? How many times was the condition met, but the prediction was wrong, and so on. It's just a simple scorecard.
And right from that table, we get our first and most obvious metric, accuracy. It asks a really simple question. When this rule fires, how often is it actually right? It's probably the most straightforward way to measure how well a rule is doing. Next up is precision. And I like to think of this one as measuring purity. It's asking, of all the things my rule flagged, how many were actually the real deal? High precision is what you want when you can't stand false alarms. You want to be sure that when it flags something, it's right. And rounding out the big three is recall, which is all about completeness. This one asks, of all the things I should have found, how many did I actually catch? High recall is absolutely critical when you can't afford to miss anything. Think about something like medical screening. You want to find every single potential case. Okay, everything we've talked about so far kind of assumes our data is in one big flat table. But you and I both know that's not how the real world works, right? Real data is messy. It's usually spread out across a bunch of different tables in a relational database. So how on earth can a simple if-then rule handle that kind of complexity? Let's jump back to our train example for a second. In a real database, you're not going to have one giant spreadsheet with all the train info.
No way. You'd probably have a trains table and then a totally separate cars table, and they'd be linked by a relationship, right? A train has cars. The key information we need is spread across that whole structure.
So here's the answer. It's a much more powerful technique called Inductive Logic Programming, or ILP for short. This is a type of rule learning that was built from the ground up to handle relational data. It's smart enough to actually learn rules that can follow those relationships between your tables. And that means it can find much, much deeper patterns in the structure of your data.
And here's the absolute key difference. A simple propositional rule just checks a property that's already there, like has short car. It's a simple true-false. But an ILP rule, it can reason about the relationships themselves. It can say something way more complex like, look for a train T, where there's a car C, and that train T has that car C, and the car C's length is short. If you've ever written SQL, that should sound familiar. It's basically learning the logic of a database join all on its own.
So, to put it really simply, ILP is what allows machine learning to speak the language of relational databases. See, instead of making you flatten out all your data and lose all that valuable structural information just to feed it to a model, ILP uses that structure to its advantage. And this is what lets it find those really deep, interesting patterns and build powerful rules from the complex data you're already working with.
All right, let's wrap this up. We started with this fundamental need for AI we can actually explain. Then we saw how symbolic machine learning can build those transparent if-then rules with things like the covering algorithm. And now we've seen how a technique like inductive logic programming takes that whole idea and scales it up to handle the complex, multi-table databases that, let's be honest, run the world.
Hey, if this explainer helped you get a better handle on the logic behind explainable AI, do us a quick favor and hit that like, share, and subscribe button. It really helps us keep making more deep dives just like this one.
So I'll leave you with one last thing to think about. As AI gets more and more powerful and weaves itself into every part of our lives, being able to explain why it does what it does, well, that stops being a nice-to-have technical feature and becomes the absolute bedrock of trust. Because really, if your most powerful AI can't tell you why, can you truly trust its answer?